So for Worksheet 1.8 we have to do a little bit of review. The first thing we're going to review are the rules for parallel circuits. And of course we always start with rule number 1, and this is in regards to all the circuits that we're analyzing. And the first step is we have to determine whether the circuit's series, whether the circuit is parallel, or if it's a combination of series and parallel. And we do that by just simply observing the path for electrons to flow. Notice this one is a series circuit. It has only one path. This circuit here has two paths for the electrons to travel down. So therefore it's parallel. And then the last circuit I have drawn here is a combination. We have this resistor here as only one path, so it's in series. Once the electrons get through that portion of the circuit, then they have a choice. They can either take this branch or they can go down here to this branch. So therefore that is a combination circuit. Rule number 2 for a parallel circuit. The first statement is current divides as an inverse proportion to the resistance of the branches. That might be a little bit of a confusing way for us to state it. I prefer the second bullet point here as a much better way to think about it, is the total current flow in the circuit is equal to the sum of the currents through all of the branches. This is known as current adds. So what this rule tells us is that if we take all of these current values located here in this circuit, we add those together, we will end up with 25 amps of current. And regardless of which conductor we're looking at, whether it's this conductor or this conductor, 25 amps of current is going to return back to the source. So it's important to understand that, and this is one of those basic rules that are so important for us to remember as electricians, because every time we add a load, if we think of these resistors as light bulbs, every time we add another load, every time we add another light bulb, our current continually builds, and occasionally that current can get too high, or there will be an imbalance either on the hot or the neutral, which will ultimately lead to a problem for us. Rule number 3 is probably the easiest rule to remember, and that is that voltage always remains the same across each of the branches of the circuit. So no matter where you measure the voltage in a parallel circuit, it will always be the same. So if you are using your voltmeter and suddenly you have some strange voltage that you did not start with, so in this case we'll start with 120, and we came down here to this location right here. If we measured that voltage there and maybe we got, say, 95, obviously there is something wrong with the circuit at that point. So that would be a good indication, because we should not have 95, we should have 120. Here again in Rule 4, I kind of re-emphasize the total current again. And again, what are we doing? We're adding light bulbs, we're adding loads, we're just simply adding more devices to an existing circuit. And so in this case we're just going to add 10 to 8 and add 12 and add 25, and again we end up with 55 amps, because we're measuring current, the speed at which the electrons flow. And so since we have 55 amps returning here on this wire, we should, if our circuit is functioning properly, have 55 amps on our wire that leaves our source here. Alright, rule number 5, we're starting to get into resistance. Rule number 5 simply tells us that total resistance must be less than the smallest branch resistance. So when you do your calculations and you come up with a resistance total, you have to look at that resistor value and then hopefully you understand the old alligator or crocodile mouth, and notice which way the crocodile mouth is pointing. It's less than any of the other resistor values. So the resistance total is always going to be less than the smallest branch resistance. So here's our first formula we use to determine resistance total. So I'm looking for resistance total over here. And in this case, I only have the ability to use 2 resistors at a time. So sometimes this isn't the most speediest of formulas to use. However, if we don't have a scientific calculator, it sometimes is the best choice because we don't have to necessarily get down to the whole decimal thing for the reciprocal formula. So what we're going to do is we're going to do R1, we're going to do R2, we're going to multiply them together, and then of course this line means division, so then we're going to divide that answer by the same value R1 added to the value of R2, and that will give us a new resistor value which we can just call Rx. So then if we have more than 2 resistor values, then we might have to go to, say, like Rx, and we're going to multiply that by, say, R3, and then we'll just divide that by Rx plus R3. And we just simply keep paring those down until ultimately we end up with this value right here, which is our resistance total. And then we have our reciprocal formula. So again, we're solving for our total resistance, and we know that it's going to be less than any of these resistor values again. So at the end we're going to do that comparison. We have to know whether that's less than any of those resistor values. And this formula is easy, especially if you have a scientific calculator. You're going to ultimately end up using your brackets, and so you'll put this information in brackets so that the calculator does that operation first, and then it will divide it by 1, and you will ultimately end up again with our resistance total over here. Here's the formula we use for determining if we need to find an unknown resistor. I'm just going to clean that up just a little bit. Those lines should be in that location. And all that's changed is we have now 1 is over, and notice what we're doing. We start with the total, and now we are actually subtracting R1 minus 1 over R2, and so in this case this could be resistor value number 3 that we're solving for in this case. Okay, now we're going to go through number 1 and number 2 from worksheet 1.8. Just a couple of parallel problems here, and notice first thing we had to determine, is it a parallel circuit? So back to our rules again, more than one path, so it's a parallel circuit. So we know that our resistance total therefore has to be less than the rest of the resistors. So in this problem I have 1K and I have 20K. So I went ahead and did my conversions right away. I converted 1K to 1,000, and I converted 20K to 20,000, and I went ahead and typed that into the calculator, and let's see what we get. So the answer to number 1 is going to be 952.3 ohms. So then we go down here to number 2, same procedure. I analyzed the circuit. We're looking at multiple paths again for current to flow, so therefore it's a parallel circuit. I go ahead and I look at my resistor values, put those into the equation up here, And it's always helpful for me to write the equations out and then go ahead and enter that into the calculator, and let's see what we come up with. So I put that into the calculator, and the answer to number 2 is going to be resistance total equals 41.6. Now, one thing I wanted to mention here, I've got this OR down here. Notice what I did. I used the product over sum formula, and I went 500 times 100 divided by 500 plus 100, and I ended up with 83. So again, we've got some resistor values here that are equal to the others, so I could simply just do that again. I could do the 83.3 times 83.3, do that over top of 83.3 plus 83.3, and that would get me the same answer as using our reciprocal formula. So go ahead and solve the rest of those problems from worksheet 1.7 today and also 1.8. And if you have any questions, don't be afraid to ask either Mr. V or Mr. Morse.